Hello and welcome to the Deep Space Relax channel. Tonight, we gently drift into the ancient and extraordinary world of geology, the deep memory of our planet, written in stone. Long before stars were given names or oceans gained borders, the Earth was already alive, reshaping itself in silence. Mountains rose and slowly collapsed, seas disappeared and returned again. Continents wandered across glowing oceans of molten rock. The ground beneath you is older than imagination itself. And yet it is still moving, still breathing, still changing. This is the story of geology, a story of fire and water, of creation and collapse, of beauty that takes millions of years to unfold. Beneath every step, within every pebble, there are whispers of volcanoes, glaciers, and stars long gone. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, simply breathe, let your eyelids grow heavy, and allow the ancient earth to cradle your thoughts. Let us begin. Earth's crust is thinner than you might imagine. If the planet were shrunk to the size of an apple, the crust, the solid outer shell we live upon, would be no thicker than the skin of that fruit. This idea feels almost unbelievable, yet it is true. The continents and ocean floors together form a layer that, on average, reaches only about 30 kilometers beneath land, and less than 10 beneath the sea. Below that lies the mantle, a vast region of slowly flowing rock that makes up most of Earth's volume and mass. The crust floats on this mantle like fragile rafts, drifting on molten currents and reshaped by plate tectonics. Mountains, valleys, and ocean trenches are tiny ripples on the surface of an enormous sphere of stone. Everything we know, every forest, city, and ocean exists atop a layer so thin it nearly vanishes when viewed in scale. Granite once flowed like rivers of fire deep underground. Long before it hardened into the rugged stone we see today, granite was alive with heat. Deep within Earth's crust, molten magma gathered in hidden chambers, moving like slow streams of flame. Over millions of years, it cooled and crystallized into the familiar speckled rock that now forms the hearts of mountains. Each grain of quartz and feldspar once shimmered with molten light before solidifying forever. When you run your fingers across granite, you are touching the frozen remains of that ancient flow locked in time. Many of the world's great landscapes, from Yosemite's cliffs to the Scottish Highlands, were shaped by granite rising and hardening below the surface. It carries within it the patience of the planet itself, reminding us that what appears solid today was once liquid light, slowly transformed beneath unimaginable pressure into something enduring and timeless. Diamonds can form in a heartbeat when conditions align. Most diamonds take billions of years to grow deep within the mantle, born from carbon crushed and heated beyond comprehension. Yet nature can be unpredictable. Under the most extreme pressures, carbon can rearrange itself into diamond almost instantly. These sudden transformations happen miles beneath the surface, here where temperatures exceed molten metal and pressures surpass anything humans can maintain for long. When volcanic eruptions bring these gems upward, they travel through narrow pipes of rock known as kimberlites, carrying stories from the depths of Earth's creation. Each diamond you see, no matter how small, once existed in darkness and heat fierce enough to melt steel. Whether formed slowly or in a geological heartbeat, Every crystal preserves a moment when ordinary carbon became extraordinary. They are nature's perfect records of transformation, born from chaos and pressure, rising toward light through the bones of the planet. Some mountains are still rising faster than your fingernails grow. Mountains may appear eternal, but they are alive with movement. Deep beneath the surface, tectonic plates push and collide, forcing rock upward little by little. In the Himalayas and parts of the Andes, this slow collision continues to lift peaks faster than your fingernails lengthen. What feels solid is part of an endless rhythm of uplift and erosion. Wind, water, and ice wear mountains down grain by grain, while forces far below rebuild them in a cycle that has played out for hundreds of millions of years. A mountain may seem motionless, but if time was sped up, you would see it breathe, swelling upward as continents collide. The stone beneath your feet may once have rested on an ancient ocean floor, carried skyward over vast ages. These giants remind us Earth is never still, but constantly reshaping itself even while we sleep. Entire continents float like rafts on molten rock. The ground beneath us drifts on a hidden sea of heat. Beneath the crust lies the mantle, a region so hot that solid rock behaves like an incredibly slow-moving liquid. Continents rest on this mantle as massive rafts of rigid stone, drifting across it through time. They slide, collide, and separate at speeds of only a few centimeters per year. Yet over millions of years, those tiny movements reshape the world. Oceans open and close, mountain ranges rise, entire climates transform. The continents we know are travelers, always in motion, though the journey is invisible to us. This slow drift once united all land into the supercontinent Pangaea, and will one day bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers on vast drifting plates, carried across geological seas without ever sensing the motion. Earth's surface is constantly recycling itself through plate tectonics. Nothing on the planet's surface is permanent. The continents and seafloors we see today are part of an endless cycle of destruction and renewal known as plate tectonics. Where plates collide, mountains rise. Where they separate, new ocean crust forms as molten rock wells upward. Elsewhere, one plate dives beneath another and sinks back into the mantle, melting and becoming part of Earth once more. Even the ground beneath the oceans is born, spreads outward, and disappears on timescales of tens of millions of years. Every grain of sand, every cliff, every volcanic plain belongs to this great planetary cycle. Earth is the only world we know that recycles itself so completely, using the slow power of heat and gravity to keep its surface young. Planet skin is never truly still, forever shedding and remaking itself in quiet, graceful motion. The Himalayas are still growing taller every single year. High above the clouds, the Himalayas continue to rise. Their growth began around 50 million years ago when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision has never stopped, pushing the mountains upward by a few millimeters each year. The peaks may appear timeless, but their summits climb steadily toward the sky, even as wind and glaciers carve them down. Every tremor in the region, every deep earthquake, whispers of the immense pressure still at work. These mountains are not relics of the past, but living results of an ongoing collision that began long before humans existed, and the same force that built Everest continues to reshape the land beneath millions of people. In their silent rise, the Himalayas remind us that Earth's power is patient, relentless, and always in motion, sculpting continents as easily as clay. Continents drift as fast as your hair grows. If you measured the movement of a continent, it would advance at roughly the same pace as your hair lengthens in a month. Yet over geological time, that small speed reshapes the entire face of the planet. Continents slide across the mantle, carried by convection currents deep inside Earth. The Atlantic Ocean grows slightly wider each year, while the Pacific slowly shrinks. In millions of years, today's maps will become unrecognizable. Africa will move closer to Europe. Australia will edge northward, and continents may once again merge into a single giant landmass. This slow drift connects fossils found oceans apart and explains why mountain ranges on distant continents share common origins. The ground feels solid, yet it is part of a vast, restless voyage that has never stopped since the planet was born. The ocean floor is younger than most of the continents. Beneath the waves lies a hidden world in constant renewal. While the continents preserve rocks that are billions of years old, the seafloor is surprisingly young. Along mid-ocean ridges, molten rock rises, cools, and becomes fresh crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches, where one plate slides beneath another. This recycling means no ocean crust survives longer than about 200 million years, a brief moment in Earth's vast story. The continents, by contrast, are ancient survivors, floating above the cycle of destruction. If you could watch the planet's surface over time, you would see oceans appear and vanish in a rhythm like breathing. The seafloor is the planet's heartbeat, renewing itself endlessly, a reminder that even the deepest, darkest places on Earth are alive with motion and change. Magnetic stripes on the seafloor record Earth's ancient flips. Across the broad plains of the ocean floor, rocks are patterned like a barcode. These alternating magnetic bands mark times when Earth's magnetic field reversed, with north and south swapping places. As new crust forms at mid-ocean ridges, minerals in the lava align with the planet's magnetic field before cooling locks that direction in place. Millions of years later, another reversal leaves the next band, pointing the opposite way. By reading these stripes, scientists trace a history of magnetic flips stretching back tens of millions of years. This discovery became one of the keys that confirmed plate tectonics, showing how the seafloor spreads outward through time. Beneath the oceans lies not chaos, but a beautifully ordered record of invisible forces written in stone by magnetism, heat, and the slow pulse of geological time. Rocks can become magnets after cooling from lava. When molten rock cools at Earth's surface, something remarkable happens. Tiny grains of iron and nickel inside the rock line themselves up with the planet's magnetic field like unseen compass needles. Once the lava hardens, those directions are sealed in, preserving a snapshot of magnetic orientation at that exact moment. Geologists study these natural magnets to map the shifting history of Earth's poles. Every reversal, every wandering motion of magnetic north is captured in stone as the planet's molten skin solidifies. These magnetic fingerprints helped prove that continents drift and seafloors spread. In every volcanic rock lies a silent record of Earth's magnetic heartbeat, offering clues about ancient directions and the invisible forces shaping the space around our world. The planet's memory is magnetic, written into the iron heart of stone. Every volcano connects to a hidden magma chamber. Far below the surface, each volcano has a core that beats with molten fire. Underground magma chambers are vast reservoirs of liquid rock, feeding eruptions that can reshape landscapes and even alter climates. Some chambers are small and shallow, others immense and deep, reaching far beneath the crust. Inside, crystals grow, gases rise, and pressure builds until the rock above can no longer hold it back. Then, with staggering force, the chamber releases its energy through cracks and vents, pouring lava and ash across the world above. Between eruptions, these reservoirs remain concealed, slowly refilling and evolving. Modern technology lets scientists glimpse their shapes by reading seismic waves, like an ultrasound of the Earth. Each volcano belongs to this deep-breathing network, reminding us that beneath calm fields and sleeping peaks, vast glowing worlds of molten stone are waiting quietly below. Some volcanic eruptions last for hundreds of thousands of years. Not every eruption is a sudden, explosive moment. Some are patient and relentless, flowing for ages beyond imagination. When mantle plumes release enormous volumes of magma, the result can be flood basalt, a massive outpouring of lava that continues for hundreds of thousands of years. These events can bury entire regions beneath miles of solid rock. And the Deccan traps in India and the Siberian traps in Russia are immense relics of such ancient fire. During their long reign, they released enough gas and heat to alter climate and shift the course of life itself. Standing on those hardened lava plains today, it is difficult to imagine molten rivers stretching to every horizon. They remind us that sometimes Earth reshapes itself, not with single explosions, but with the slow, unstoppable rhythm of fire spreading across open sky. Basalt covers most of the ocean floor in dark, dense layers. If you could walk along the bottom of the sea, each step would land on basalt, a heavy, dark rock born of fire. It forms when molten material from the mantle erupts along mid-ocean ridges and cools quickly in seawater. The result is a vast, continuous crust spanning ocean basins like the planet's armor. Unlike the lighter rocks of continents, basalt is rich in iron and magnesium, giving it its deep color and weight. Its layers renew continually as the seafloor spreads, while older sections sink back into the mantle and melt again. Every square inch of ocean floor has joined this endless cycle of creation and destruction. Beneath the waves, basalt holds the history of Earth's most patient movements, layer upon layer of cooled magma forming the quiet foundation of the world's oceans. Pillow lava freezes into shapes like underwater balloons. When lava erupts beneath the ocean, it cools so fast that the outer skin hardens instantly while molten rock still pushes from within. This strange process creates rounded forms that resemble pillows or bubbles stacked together. These smooth, bulbous structures, called pillow lava, can blanket wide stretches of seafloor. Each pillow is a snapshot of fiery motion captured in an instant, showing how molten rock meets cold seawater. When explorers find pillow lava on land, it tells them the region was once deep underwater. The sight is eerie and beautiful, as though the stone still remembers flowing like liquid before being sealed by the chill of the sea. These shapes are geological sculptures of time, proof that even in the dark, crushing depths, the planet's creative forces remain alive and at work. Obsidian is volcanic glass cooled in an instant. In explosive eruptions, lava can cool so rapidly that crystals never have time to form. The result is obsidian, natural glass, with a dark, gleaming beauty. It is smooth, sharp, and reflective. It created when molten rock meets cold air or water and solidifies almost instantly. For thousands of years, people prized it for its razor edges, shaping blades, tools, and ornaments. Yet behind its mirror-like surface is a tale of extreme change. Molten fire arrested mid-motion. Heat turned into fragile stone. Obsidian breaks easily, but its fractures reveal elegant curved patterns called conchoidal fractures, as if each break still echoes the lava's original flow. This glassy rock is one of geology's sharpest contrasts, born in violence yet perfectly still, delicate yet ageless, a piece of fire caught forever in stone. Some rocks preserve bubbles of Earth's ancient atmosphere. Trapped inside the tiniest hollows of stone, scientists have found microscopic bubbles of air that have survived for millions of years, and these preserved pockets act like time capsules, sealing the chemical signature of past atmospheres. By studying them, researchers learn what gases once filled the sky, how much oxygen existed, how much carbon dioxide warmed the planet, and how volcanic activity or life itself changed the balance. Some bubbles formed in cooling lava, others within sediments or ice. Each contains an echo of an ancient breath, a ghost of the air that surrounded early forests, giant reptiles, or even the first creatures to inhale. To hold such a rock is to hold a fragment of vanished sky, a delicate record of the ever-changing air that connects all living things across Earth's long history. There are mountains higher than Everest, hidden beneath the sea. Far below the surface lie mountain ranges that dwarf the world's tallest peaks. Along mid-ocean ridges, immense chains of volcanic mountains stretch for tens of thousands of miles, rising higher from base to crest than Everest rises above sea level. These submarine ranges are mostly unseen, shrouded in darkness and crushing pressure. Yet they are among the most active regions on Earth. Lava continually emerges from fissures, building new peaks and valleys in slow, steady motion. Some hidden giants, such as Mauna Kea, when measured from its underwater base, surpass even the great Himalayan summits. They remind us that much of Earth's grandeur lives unseen beneath the waves, vast silent kingdoms of rock that grow and shift in darkness without ever seeing the sun. Earth's deepest point is nearly as far below sea level as planes fly above it. In the Pacific Ocean lies the Mariana Trench, in a chasm so deep that if Mount Everest were dropped into it, the summit would still lie more than a mile beneath the surface. Its deepest known point, the Challenger Deep, reaches nearly 7 miles down, almost the same distance passenger planes travel above Earth. Down there, pressure is immense, strong enough to crush steel. Yet even in that darkness, life persists. Strange organisms glow in black water, thriving among mineral-rich sediments. The trench marks a subduction zone, where one plate slips beneath another and sinks back into the mantle. It is not only the lowest point on Earth, but one of the planet's engines of renewal, reminding us how small the visible world is compared to the vastness hidden below. The planet hums with micro-earthquakes you never feel. Even when the ground seems perfectly still, it vibrates with a faint murmur of constant motion. Across Earth, thousands of tiny quakes ripple through the crust each day, too small for humans to notice. These micro-earthquakes release little bursts of energy as the planet adjusts to stresses far below. Scientists use sensitive instruments to record these whispers, creating detailed maps of shifting faults and hidden magma flows. Together, They form a background hum that never truly stops, the quiet pulse of a living planet. This ceaseless trembling tells geologists where faults are creeping, where pressure is building, and where volcanic systems are stirring. The stillness of the world is an illusion. Beneath every mountain, forest, and sea, the planet moves in countless subtle ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of Earth's restless heart. Earthquakes can make entire rivers run backward. When the ground shakes with enough force, the landscape itself can change direction. During powerful earthquakes, land can tilt or shift so abruptly that rivers are forced to reverse their flow. This rare phenomenon has been recorded in events such as the Great New Madrid earthquakes of the early 19th century, when sections of the Mississippi River temporarily flowed upstream. Sudden movement can lift one side of a fault or drop another, creating natural dams or lowering valleys. For a brief moment, the planet's inner power can overpower gravity's steady pull that guides every drop of water. When balance returns, rivers carve new routes through altered terrain, and these moments reveal the sheer strength of geological motion, showing that even something as constant as a river can be turned backward by hidden forces deep within Earth. Some faults creep silently without shaking at all. Not all tectonic motion arrives with trembling and destruction. Along certain fault sections, the crust slides so slowly and smoothly that no noticeable shaking reaches the surface. This quiet movement, known as fault creep, releases pressure in small continuous increments. It is invisible to anyone standing above, yet measurable with instruments that detect motion of only a few millimeters per year. Some faults in California and Turkey move this way, gliding gently while neighboring sections remain locked and tense. Creeping portions may prevent large quakes in those areas, but they can also transfer stress elsewhere. This subtle dance between tension and release is part of the planet's constant balancing act. Even without drama, the ground is shifting, whispering in slow motion as Earth adjusts itself grain by grain across the ages. Earth's core is hotter than the surface of the Sun. At the planet's center lies a sphere of solid and molten metal under pressures beyond comprehension. Temperatures there rise above 9,000 degrees Fahrenheit, rivaling and even exceeding the Sun's visible surface. This immense heat is leftover energy from Earth's formation, combined with the steady decay of radioactive elements deep inside. Though we will never see it directly, the core drives everything from volcanic eruptions to the magnetic field that shields life from cosmic radiation. Its motion churns like a dynamo, generating invisible lines of force that reach far into space. The inner core, solid iron, rotates slightly faster than the layers above, while the outer core flows as liquid metal. This hidden furnace is Earth's beating heart, the power source that keeps our world alive with movement, warmth, and quiet resilience. There may be an entire ocean hidden deep inside the mantle, far beneath the crust, where rock glows with heat and pressure. Scientists have found minerals holding vast amounts of trapped water. These discoveries suggest an ocean's worth of water may exist hundreds of miles down, bound within crystal structures rather than flowing freely. If released, this hidden reservoir could fill the world's oceans many times over. It is not a sea in the familiar sense, but a deep storage of the same substance that sustains all life. Tectonic plates may carry water downward into this realm, only for it to return through eruptions and rising plumes of molten rock. This unseen cycle may be one key to understanding why Earth has oceans at all. Even within the deepest stone, water finds a way to endure, waiting patiently inside the mantle for eons. Crystals can grow larger than a person inside underground caves. In the quiet darkness beneath the deserts of northern Mexico, there is a cathedral of crystal. The Cave of the Crystals, buried deep inside a silver mine, holds translucent gypsum blades stretching more than 30 feet long. Each one took hundreds of thousands of years to grow in perfect stillness, nourished by hot, mineral-rich water that once filled the chamber. When the water drained away, the crystals remained, shining like frozen moonlight in the heavy, humid air. Entering the cave feels like stepping into another world, built not of rock and fire, but of slow, delicate perfection. The conditions needed to create such giants are almost impossibly rare, balanced between heat, saturation, and time. These enormous crystals remind us that even the hardest materials on Earth can shift and change, given patience enough. They are the planet's most beautiful expression of stillness, shaped by time. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. Deep below the surface, where heat and humidity can overwhelm equipment in minutes, lies one of the most breathtaking sights ever discovered. The Cave of the Crystals, found by miners in the year 2000, contains gypsum formations so large they resemble pillars of light. Some weigh dozens of tons and span the chamber like colossal beams of glass. They formed when mineral-rich groundwater held a steady temperature for hundreds of thousands of years, allowing molecules to arrange themselves with perfect symmetry. When the cave was drained, the growth stopped, freezing the scene in place. The air is so hot and thick that no one can stay inside for long. Yet, for brief moments, explorers have walked among walls of translucent stone. It is a vision of geological art created not by hands, but by time, water, and the quiet chemistry of the earth itself. Salt domes can pierce through rock like slow-motion explosions. In regions where thick layers of ancient salt lie buried beneath heavier rock, a strange and powerful process can unfold. Over millions of years, the salt begins to flow upward, driven by pressure from the surrounding layers. Though solid, salt behaves like a viscous fluid under great stress. It rises through the rock above, bending and fracturing it, creating dome-shaped structures that can reach miles in height. These salt domes can trap oil and gas, forming reservoirs that have shaped entire industries. From above, they look like gentle swells in the land, but beneath the surface, they are vast pillars of slow movement, reshaping the earth in silence. Each one carries the story of ancient seas that evaporated long ago, leaving minerals that still climb skyward. Proof that even solid ground can flow like a patient, unstoppable tide. Petrified wood is quartz, replaced atom by atom. What looks like a fallen tree turned to stone is something far stranger and more delicate. When a tree is buried by volcanic ash or sediment, minerals carried by groundwater seep into its cells. Over thousands of years, each tiny structure of wood is replaced molecule by molecule with quartz, preserving every ring, knot, and fiber in astonishing detail. The result is a fossil that still resembles wood, yet feels cold and heavy in the hand. Sometimes, trace elements stain it in reds, yellows, or greens, painting natural artwork through its grain. Holding petrified wood, is like holding a memory made solid, a living thing transformed into crystal by the patience of time. Nature's way of saying that nothing truly disappears. It only changes form, keeping the story of life locked inside stone. Coal began as ancient forests trapped in swampy worlds. Long before humans walked the earth, vast tropical forests covered much of the land. Even when these forests died, their trunks and leaves sank into oxygen-poor swamps where decay slowed almost to nothing. Layer upon layer of plant matter accumulated, pressing down beneath its own weight. Over millions of years, heat and pressure transformed that buried organic material into coal, a dense rock made of concentrated carbon. Within every piece lies sunlight, captured by plants under a prehistoric sky. Burning coal releases that ancient light again, a ghostly return of energy stored for eons. The process that formed it tells a story of transformation, where life became stone and sunlight became fuel. Every lump of coal carries the imprint of vanished forests, the breath of an old world condensed into dark, glittering veins beneath our modern one. Oil comes from the buried remains of ancient plankton. Long before dinosaurs roamed land, oceans teemed with microscopic life. When those tiny organisms died, they sank to the seafloor and mixed with mud, forming thick layers of organic sediment. Over millions of years, the weight of water and rock pressed them deeper, heating and compressing them until their carbon-rich remains turned into liquid hydrocarbons. Trapped in porous rock, these ancient molecules became the oil that powers modern civilization. Every drop we burn once drifted through a primordial sea, gathering sunlight through the simplest forms of life. In a sense, the energy fueling our world is sunlight from Earth's deep past, stored beneath miles of stone. The story of oil is not only geology, but biology, chemistry, and time woven together in quiet darkness below the surface, waiting to be found. Every grain of sand tells the story of a vanished mountain. Each tiny grain once belonged to something far greater. Before it lay on a beach or desert, it was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice ground that rock into its smallest pieces, carrying them through rivers and seas. A single grain may have tumbled through glaciers, flowed down canyons, or drifted across oceans before coming to rest. Under a microscope, its shape and makeup reveal what kind of rock it came from and the journey it took. Some grains still sparkle with quartz from ancient continents. Others are volcanic shards from eruptions long gone. Every handful of sand is a storybook of time, a collection of broken worlds reduced to glittering fragments that will one day be pressed back into stone. And the cycle will begin again. Desert sand can sing with a low musical note when it moves. In a few rare deserts, shifting dunes create a deep, resonant hum that can last for minutes. These singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula, produce notes so pure they sound like the voice of Earth itself. The sound comes from countless grains sliding and colliding in unison, vibrating at a frequency somewhere between a cello's tone and a distant, thunderous roar. Scientists believe the grains must be nearly uniform in size and perfectly dry for the effect to appear. Travelers describe it as haunting, as though the dunes are breathing or speaking. Ancient peoples often treated the sound as mystical, believing it came from spirits or gods of the desert. In truth, it is physics and friction working together, turning the landscape into a natural instrument that plays the slow, patient music of a shifting world. Some beaches are made entirely of tiny shells. Along certain coastlines, the sand beneath your feet was not carved from stone, but built by life. Over centuries, the shells of countless tiny marine creatures, such as mollusks and foraminifera, broke down into fragments so fine they look like powdered ivory. These biological sands can shine white in sunlight, blush pink from crushed coral, or shimmer golden from the remains of microscopic algae. Each grain is a piece of something that once lived. The ocean's past returned to shore. Walking such a beach can feel like stepping through the ruins of invisible kingdoms, where waves and tides have turned the architecture of life into a soft, shifting tapestry. And the world's most famous white beaches, like those in the Bahamas and the Maldives, are living proof that time and biology can build beauty as surely as rock and fire. There are black, green, pink, and even red sands on Earth. Not all beaches glow gold or white. Some are black from cooled lava, others green from olivine crystals, pink from coral, or red from eroded volcanic rock. Each color tells a geological story about its source and the forces that shaped it. Black sands often rim volcanic islands, formed when molten lava met the sea and shattered into glassy fragments. Green beaches appear where rare mantle minerals wash ashore. Pink hues come from crushed shells and coral mixed into pale sand, while red sands are tinted by iron-rich rock oxidized over time. To walk these colorful shores is to wander through the planet's own palette. Every wave rearranges grains that remember fire, water, and time, blending Earth's elements into living art that shifts under the ever-changing light of the sky. Glaciers carve landscapes like moving rivers of rock. A glacier appears still, yet it flows. Over centuries, the weight of accumulated snow compresses into dense ice that slowly slides downhill, reshaping everything in its path. These frozen rivers grind against mountains, scraping valleys, polishing stone, and hauling debris for miles. When they retreat, they leave wide, U-shaped valleys, scattered boulders, and shimmering lakes that fill their abandoned tracks. The fingerprints of glaciers can be found on nearly every continent, from the smooth granite domes of Yosemite to Norway's carved fjords. Even now, glaciers continue their patient work, ungrinding ancient rock into fine dust that drifts on the wind. They are sculptors of continents, artists of time and temperature, shaping land grain by grain. In their quiet persistence is a reminder of Earth's delicate balance, where even the coldest forces can flow with power strong enough to change the world. Some glaciers move fast enough to be seen shifting by the hour. Although glaciers usually creep at inches per day, a few flow so quickly their movement can be noticed within a single afternoon. These fast rivers of ice surge when meltwater lubricates the ground beneath, reducing friction and letting massive sheets slide forward. In Greenland and parts of Alaska, scientists have recorded glaciers racing ahead at startling speeds, their fractured surfaces groaning and cracking as they go. From afar, and the motion seems impossible, solid ice behaving like liquid stone. Yet this movement carries enormous force, reshaping valleys and transporting rock by the ton. Their sudden surges remind us that even in frozen stillness, glaciers are alive with motion. To witness one in movement is to see time itself accelerate, Earth's slow rhythm condensed into a visible, breathtaking push. Ice under pressure behaves like slow-flowing honey, Beneath a glacier's surface, where pressure is immense and temperatures hover just below freezing, ice stops acting like a rigid solid. Instead, it flows, slowly but continuously, folding and bending, like honey poured in slow motion. Crystals within the ice deform and slide past one another, allowing entire masses to creep downhill. This is what gives glaciers their fluid grace, and their ability to carve mountains and shape valleys over tens of thousands of years. Under the right conditions, even solid rock can behave in similar ways over geological time. Laboratory experiments showing ice deform under pressure reveal how matter blurs the boundary between solid and liquid. What seems unyielding becomes supple with enough time and weight. The planet's greatest changes often happen not in sudden bursts, but through quiet persistence as materials learn to move under pressure. Fossils can capture raindrops that fell hundreds of millions of years ago. Sometimes, the smallest traces of the past survive in stone. On slabs of ancient sedimentary rock, scientists have found delicate impressions of raindrops that struck soft mud long before humans existed. Each tiny crater records a moment in time, a storm passing over a primeval landscape, droplets scattering across a world of strange plants and early life. Within seconds, the marks were buried beneath new sediment, sealed in darkness as the layers hardened into rock. When the surface is exposed again, it reveals a perfect imprint of weather from a vanished age. These fossil raindrops remind us that even fleeting moments can last forever when preserved by chance. In a single stone, we can read the touch of a storm that ended hundreds of millions of years ago, its rhythm still visible on the pages of the planet's memory. Some fossils preserve soft tissues, even colors and feathers. For centuries, people believed fossils captured only bones and shells, the hard remains of ancient creatures. But discoveries in recent decades have revealed something astonishing. Under rare conditions, even delicate tissues can survive. In certain rocks, scientists have found impressions of skin, muscle, and feathers, sometimes with traces of pigment that hint at the original colors of dinosaurs and early birds. These fossils form when mineral-rich water seeps through remains before decay destroys them, replacing organic molecules with stone. The result is life turned into sculpture, preserved in extraordinary detail. Some even retain microscopic structures that suggest how these animals moved, breathed, and shimmered beneath their ancient sun. To hold such a fossil is to bridge worlds, feeling an echo of warmth and color from beings that vanished hundreds of millions of years ago. Stromatolites record the oldest known life on Earth. Long before animals or plants evolved, simple microbes built layered structures in shallow seas. These formations, called stromatolites, are among the planet's oldest living fossils. They were created by mats of bacteria that trapped and bound sediment, forming domes that slowly grew towards sunlight. Some ancient examples are more than 3.5 billion years old, making them among the earliest evidence of life anywhere. Remarkably, stromatolites still exist today in a few remote places, such as Shark Bay in Australia, where microbial communities continue their slow, rhythmic growth. To look at one is to peer into the dawn of biology, when the first cells began shaping the planet. They remind us that life's story began not with speed or complexity, but with patience. Layers of living film turning light, water, and time into the foundation of everything that followed. Earth once turned completely white during a global snowball Earth, around 700 million years ago, our planet may have nearly frozen solid. Ice stretched from pole to equator, sealing oceans beneath miles of frozen crust and reflecting sunlight back into space. Scientists believe volcanic activity, changes in atmospheric gases, and shifts in solar energy combine to trigger this global deep freeze. For millions of years, Earth became a silent world of ice, its surface shining white beneath a dim sun. Yet life endured, hidden in pockets of liquid water, beneath glaciers or near volcanic vents. Eventually, eruptions released enough carbon dioxide to trap heat again, thawing the planet in a dramatic, world-spanning melt. Yet the return of open oceans may have helped spark an explosion of complex life. Snowball Earth stands as one of the greatest transformations in planetary history, a near-death and rebirth written in ice and snow. Volcanoes may have ended that frozen age with a greenhouse surge. During the depths of the global freeze, volcanoes continued to erupt, pumping carbon dioxide into the air for millions of years. With the oceans sealed beneath ice, this gas could not dissolve as it normally would, so it accumulated in the atmosphere, trapping heat. When the ice finally began to melt, the shift accelerated dramatically. Dark, newly exposed rock absorbed sunlight, magnifying the warming. Within a geological blink, the planet moved from frozen white to steaming blue-green seas once again. This thaw unleashed floods, erosion, and perhaps chemical changes that nourished early life. In a sense, volcanoes may have saved the planet, their quiet persistence beneath the ice keeping Earth's climate from dying. What had been an age of silence became one of rebirth, proving that even in the planet's deepest cold, fire and renewal were waiting patiently below. Oxygen in the air was first made by ancient microbial mats. The air we breathe owes its existence to tiny organisms that lived billions of years ago. These microbes, ancestors of modern cyanobacteria, thrived in shallow seas and used sunlight to split water molecules, releasing oxygen as a byproduct. Over time, their waste transformed the planet. At first, oxygen reacted with iron in the oceans, forming vast deposits of rust-colored rock, and only after these minerals were saturated did the gas begin to fill the atmosphere, slowly turning it into the life-giving mixture we depend on today. This event, known as the Great Oxidation, changed everything. It allowed complex cells to evolve and eventually made possible the rise of plants and animals. Every breath you take is a gift from those ancient microbes whose simple chemistry turned a barren world into a living one, paving the way for forests, oceans, and all that followed. Iron formations mark the moment the planet began to breathe. In ancient seabeds around the world lie bands of red and grey rock that shimmer with metallic luster. These banded iron formations are the fossil record of the time when oxygen first appeared in Earth's atmosphere. As primitive microbes began producing oxygen through photosynthesis, and the gas reacted with dissolved iron in the oceans, creating rust-like minerals that settled to the seafloor in layers. Over millions of years, those sediments hardened into stone, capturing the breath of a newly awakening planet. Today, the same formations are mined for iron, the backbone of modern industry. Yet they began as the byproduct of microscopic life. Each stripe in the rock is a heartbeat in Earth's transformation, marking the slow shift from a world without breathable air to one rich with oxygen, where life's chemistry could finally spread across land and sea. There was once a time when the seas were purple. Before oxygen filled the air, Earth's oceans likely looked very different. The water may have glimmered in reds and violets, colored by ancient microbes that use sulfur compounds, not oxygen, to harvest sunlight. These organisms thrived in chemically rich seas beneath an orange-tinted sky, producing pigments that stained the water with strange hues. As photosynthetic bacteria began releasing oxygen, these purple oceans slowly faded into the blue we know today. The shift from a sulfur world to an oxygen world was among the greatest transitions in Earth's history, changing everything from the atmosphere to the chemistry of rocks. For a time, though, our planet shone in colors we can barely imagine. Seas of violet under a dim sun, the signature of life experimenting with light long before forests, reefs, or air-breathing creatures existed. Entire mountain ranges have vanished without a trace. The continents we see now are only the latest version of Earth's face. In deep time, whole mountain ranges have risen and then eroded so completely that almost no trace remains. Wind, water, and gravity work patiently, wearing down even the tallest peaks, grain by grain. Sometimes, the roots of those ancient mountains survive as crystalline rock buried beneath newer layers, clues for geologists to uncover. Some of the oldest continental crust once carried enormous ranges that are now reduced to flat plains. Over hundreds of millions of years, erosion can erase a mountain as easily as waves smooth a pebble. The planet is always rebuilding itself, and what looks eternal to us is only a temporary sculpture in geology's ongoing art. Every plain and valley was once a summit, and every stone carries the ghost of a vanished mountain at its core. Continents have collided and split apart many times in Earth's past. Across billions of years, the continents have gathered and drifted apart like slow-moving puzzle pieces. Driven by heat rising from the mantle, the crust has folded, fractured, and rearranged itself again and again. Each collision built new mountains. Each separation opened new oceans. This process, known as the supercontinent cycle, has repeated at least half a dozen times. When continents collide, rocks are buried deep and reborn through heat and pressure. When they split, new crust forms, carrying fragments of lost worlds. The scars of these journeys appear in matching fossils and rock patterns found on opposite sides of modern oceans. The land beneath our feet is not fixed. It's part of a restless dance that never ends. Proof that the ground we stand on has traveled far, carrying the history of countless ancient worlds within its foundations. There have been at least 6 supercontinents before ours. Before Pangaea, before even Rodinia, Earth assembled and broke apart many times, forming vast supercontinents that drifted through the ages. Each had its own mountains, oceans, and climates, its own rise and fall, written into stone. Nuna, Columbia, Rodinia, Pannotia, and Gondwana are among the names given to these lost worlds, their remains scattered across the globe. When they existed, life was often microscopic, yet their formation shaped the chemistry of oceans and atmosphere. Each breakup and reunion altered evolution's path, stirring climate and shifting the planet's deep currents. The continents we know today are pieces of those ancient giants, survivors of a cycle spanning billions of years. To study them is to read Earth's autobiography across time, where even the land itself is temporary and nothing stays whole for long. Pangaea was only the most recent supercontinent. About 250 million years ago, Nearly all land on Earth gathered into a single vast supercontinent, surrounded by a global ocean. This colossal landmass, called Pangaea, stretched from pole to pole, connecting regions that are now continents apart. Its interior was harsh and dry, far from the sea's moderating influence, while its coasts teemed with early reptiles and forests. Over tens of millions of years, heat beneath the crust built pressure until cracks opened, splitting the land. The Atlantic Ocean began to form, and the continents drifted toward their modern positions. Fossils of the same plants and animals found on opposite sides of the ocean are silent witnesses to that ancient unity. Pangaea's breakup shaped modern geography and climate, setting the stage for everything that followed. It was not the first supercontinent, and it won't be the last. Only one chapter in Earth's endless drift. The next supercontinent may already be forming under the Pacific. Far beneath the waves, the slow motion of tectonic plates is preparing the next great rearrangement of Earth's surface. Scientists predict that in 200 to 300 million years, the continents may converge again into a new supercontinent. Some models suggest the Pacific Ocean will close as Asia and the Americas move together, forming a single landmass sometimes called Amasia. Others imagine the Atlantic closing instead and drawing Europe and the Americas back toward each other. The outcome is uncertain, but the process is inevitable. The same invisible currents that tore Pangaea apart are still working, shifting continents inch by inch. To imagine the world that far ahead is to realize how temporary our maps truly are. Earth is always remaking itself, and somewhere deep below, the first motions of the next supercontinent have already begun. Australia is drifting north toward Asia every single year. Far beneath Australia, the tectonic plate carrying it glides northward at a pace of a few centimeters each year. Over millions of years, this gentle movement becomes thousands of kilometers. Eventually, Australia will collide with the islands of Southeast Asia, raising new mountains and reshaping coastlines. Satellites already measure its yearly drift with astonishing precision. The motion is powered by deep convection currents in the mantle, where heat from the core moves vast sheets of rock like rafts on a molten sea. Though imperceptible to us, it reshapes maps, climates, and ecosystems. Coral reefs grow where land once lay. Deserts inch toward the tropics, and one day, new mountain ranges may rise between the two regions. Australia's slow voyage north is one of the most graceful migrations on Earth. Africa may one day split into two separate continents. Deep within East Africa, a vast rift stretches for thousands of kilometers, marking where the continent is slowly tearing apart. Volcanic activity, earthquakes, and thinning crust suggest a new ocean may eventually open there. The East African Rift is a visible reminder that continents are never truly rigid. They stretch and bend like skin over a living body. In tens of millions of years, the region, including Ethiopia, Kenya, and Tanzania, could separate from the rest of Africa, drifting eastward as its own landmass. Lakes such as Tanganyika and Malawi fill the rift's deep scars, early hints of the ocean that may one day flood in. Standing on its edges is like watching the birth of a future continent. The process is unimaginably slow, yet it is happening right now, shaping the world of tomorrow. Iceland sits directly above a tear in Earth's crust. Iceland exists because it straddles the mid-Atlantic ridge, a boundary where two tectonic plates move apart. Here, molten rock wells upward through a long lie in the crust, building new land as it cools. In the island is a crossroads of fire and ice, with glaciers beside active volcanoes. Hot springs, geysers, and lava fields reveal the restless power below. Every few years, eruptions remind residents that their homeland is still being built. Iceland's position makes it one of the few places where this boundary rises above sea level, letting scientists study plate tectonics in plain view. Iceland is a living experiment in creation, a place where Earth quite literally grows before our eyes, balanced between the frozen North Atlantic and the planet's molten heart. The Hawaiian Islands are a moving chain built by a stationary hotspot. In the middle of the Pacific, a plume of molten rock rises from deep within the mantle, punching through the crust to form volcanoes. As the Pacific plate drifts slowly northwest, each new eruption creates an island that later moves away from the hotspot, making room for another. This has formed a long chain of islands and undersea mountains, stretching thousands of kilometers across the seafloor. The youngest island, Hawaii, still glows with active lava flows, while older islands far to the northwest have eroded into low atolls. By tracing the chain, scientists map the Pacific Plate's movement over millions of years. The hotspot stays fixed, while the surface glides above it, leaving a dotted record of time and motion. Each island is a chapter in an ongoing story of creation written in molten stone. Yellowstone hides one of the largest volcanic systems on Earth. Beneath Yellowstone's forests and geysers lies an immense reservoir of magma, large enough to power one of the most formidable volcanic systems known. In the park's steaming vents, bubbling pools, and sudden eruptions of boiling water are surface clues to the heat below. Scientists monitor the region carefully, mapping hidden chambers that stretch for dozens of kilometers beneath the crust. While it is not expected to erupt anytime soon, its past explosions reshaped much of North America, spreading ash across vast distances. Today, the region breathes through its geysers, releasing pressure in spectacular bursts that hint at inner fire. Yellowstone is both a sanctuary of beauty and a window into the planet's restless nature, where beneath tranquil landscapes, ancient heat and pressure continue shaping Earth in silence. Supervolcanoes can alter the planet's climate for centuries. When ordinary volcanoes erupt, they may affect local weather for a few seasons. When supervolcanoes erupt, they can reshape the entire planet. These colossal explosions release thousands of cubic kilometers of ash and gas into the atmosphere, blocking sunlight and cooling the world for decades, sometimes centuries. Evidence appears in ash layers and climate records linked to Yellowstone, Toba, and Taupo. Aftermath can include volcanic winters when temperatures fall and ecosystems struggle to adapt. Though rare, these events remind us how delicate the balance is between Earth's interior and its surface. The power beneath our feet has shaped evolution itself, sometimes triggering mass extinctions that cleared the way for new life. Yet even in their fury, supervolcanoes belong to the planet's long rhythm of renewal, cycling materials between crust and sky, and showing how deeply life and fire are entwined. And the largest known volcanic eruption happened in what is now Indonesia. Around 74,000 years ago, a colossal eruption at Lake Toba in Indonesia changed the world. It expelled more than 2,000 cubic kilometers of ash and magma, leaving a caldera about 100 kilometers wide that is still visible today. The blast dimmed skies across the globe, lowered temperatures, and spread ash over continents. Some scientists believe it caused a brief volcanic winter that may have affected early human populations. Even after the eruption ended, gases lingered in the atmosphere, tinting sunsets and cooling the planet for years. The event was so immense it dwarfs any eruption in recorded history. Today, the calm lake filling the caldera looks peaceful, and yet beneath that quiet surface lies one of Earth's most powerful scars, a reminder that the greatest acts of creation often arrive wrapped in destruction. Some eruptions have left ash that still circles the globe today. Fine volcanic ash can remain in the upper atmosphere for years, carried by winds that loop around the planet. Particles from major eruptions, such as Mount Pinatubo in the Philippines or Krakatau in Indonesia, have been detected long after the explosions ended. These microscopic fragments scatter sunlight, creating brilliant red sunsets and slightly cooling global temperatures. High above weather, they form thin veils that reflect light in ways painters once captured after historic eruptions. Some ash layers even return to Earth much later, recorded in ice cores and ocean sediments. Every eruption, no matter how remote, connects to the atmosphere that wraps the whole world. The air we breathe can carry traces of distant blasts, a delicate reminder that even the calmest sky holds echoes of Earth's fiery breath. Lava lakes can remain molten for decades without cooling. In a few rare craters, molten rock never fully solidifies. These lava lakes, such as those at Erta Al in Ethiopia and Kilauea in Hawaii, persist because heat and magma are continuously supplied from below. Their surfaces churn like fiery oceans, crusting over only to crack apart again. At night, they glow like windows into the planet's core, orange light flickering against dark rock and smoke. The balance is so precise that these lakes can last for decades, constantly refreshed by deep circulation. Watching one is hypnotic, a living furnace breathing in slow rhythm, and they offer scientists rare clues about magma chemistry and physics that labs cannot truly reproduce. Each lake is a reminder that Earth's fire still burns just beneath its thin, cooling skin, timeless and alive. Lightning can strike inside volcanic ash clouds. When a volcano erupts, friction between ash particles generates powerful electrical charges. As the charge builds, it discharges as lightning that crackles through the plume. Volcanic lightning can light up whole skies, creating storms of fire and brightness above erupting mountains. Unlike ordinary thunderstorms, these bolts are born from rock and gas alone. Photos show branching flashes cutting through columns of black ash. Each strike lasts only a heartbeat, yet carries immense energy. Scientists study this lightning to better understand ash flow and eruption intensity, and since lightning can signal how violently material is being thrown upward. To witness it is to see Earth's elements fuse, solid, liquid, and gas meeting electricity, an awe-inspiring display where even destruction can shimmer with startling beauty. When volcanoes meet ice, they create explosive steam eruptions. Where glaciers sit atop volcanoes, heat and ice collide spectacularly. When magma rises beneath ice, it melts massive amounts of water in moments, producing steam that expands with explosive force. Such eruptions can blast through the glacier, sending floods and ash clouds racing down valleys. Iceland's volcanoes often behave this way, hidden beneath ice caps until pressure builds and breaks free. The interaction leaves behind unique landforms, ridges and plateaus sculpted by fire and water together. Scientists call some of these formations tuyas, monuments to the strange partnership of heat and cold. Each eruption beneath ice rewrites the landscape, proving that even nature's opposites are linked in a cycle of creation and transformation that has shaped Earth since its earliest days. Entire new islands have risen from volcanic eruptions within living memory. Across the oceans, new land sometimes appears where there was once only water. Submarine volcanoes occasionally erupt with such force that they build islands from the seafloor upward. In the past century, eruptions near Iceland, Japan, and Tonga have created fresh patches of land that still steam and harden under the sun. Some vanish again within years, eaten by waves, while others stabilize enough to host life. In these newborn islands reveal Earth's creative power in real time, proof that the planet is still building itself quietly and continuously, even in our own era. To watch one form is to witness the same process that built continents long ago. Birds, plants, and eventually humans make their way there, turning raw lava into living ecosystems. The birth of new islands reminds us that Earth is not finished with its work. The planet keeps building, breaking, and beginning again, renewing its surface one eruption at a time. Some lakes are filled with dissolved carbon dioxide that can erupt like soda. In parts of Africa, certain deep lakes hold enormous volumes of carbon dioxide trapped beneath their surfaces. When the balance of temperature or pressure shifts suddenly, that gas can surge upward in a deadly, invisible wave. Lake Nyos in Cameroon released such a cloud in the 1980s, suffocating life in nearby valleys. Scientists now monitor these lakes carefully and install systems that vent gas safely before pressure builds too high. The phenomenon is called a limnic eruption, a rare but potent reminder that even tranquil waters can conceal immense energy. The gas rises from volcanic sources below the lakebed, seeping upward through fractures in the crust. Over centuries, it dissolves into the water like carbonation in a sealed bottle. When it finally escapes, and the result is silent and shocking, an event as strange as it is frightening. Sinkholes can swallow buildings in seconds. Beneath many cities and fields, hidden cavities form where limestone or salt slowly dissolves in groundwater. When the roof of one of these voids collapses, the ground above can drop away without warning, opening a sinkhole. Some are only a few meters wide, others span hundreds, consuming cars, trees, and homes in moments. They form most often after heavy rain, when water seeps through cracks and weakens the layers below. Entire neighborhoods have been built atop such fragile foundations without realizing it. Scientists map vulnerable regions with radar and ground sensors to detect cavities before disaster strikes. Dramatic as they are, sinkholes are part of the planet's natural recycling of rock because water patiently sculpts the landscape from beneath. Each collapse exposes the delicate balance between solid ground and the hidden hollows that lie quietly below our everyday world. Karst landscapes hide secret rivers flowing through stone. Where limestone or dolomite dominates the bedrock, rainwater gradually carves intricate webs of tunnels and caverns. These underground systems can stretch for hundreds of kilometers, carrying entire rivers beneath the surface. The land above collapses in places, forming sinkholes, valleys, and jagged ridges typical of karst terrain. water that vanishes into a cave mouth may reappear miles away as a clear spring. In some regions, entire ecosystems have adapted to these lightless waterways. From blind fish to translucent insects, the karst landscapes exist on every continent and provide drinking water for millions of people, yet their hidden nature makes them vulnerable to pollution. Exploring them is like entering the planet's circulatory system, where stone and water move in endless dialogue, dissolving, shaping, and renewing Earth's surface drop by drop. Stalactites grow from the ceiling, stalagmites from the floor, and they can meet to form pillars. Inside limestone caves, dripping water carries dissolved minerals that crystallize as the water evaporates. From the ceiling, each droplet leaves behind a tiny ring of calcite that lengthens downward over centuries, forming a stalactite. Where the drops land, matching mounds build upward as stalagmites. In time, they can meet, creating towering columns that seem to hold the cave aloft. And the process is so slow that growth rates are measured in millimeters per century. Lantern light reveals their delicate textures, frozen waterfalls sculpted by patience. These formations are living records of a cave's history, capturing shifts in water chemistry and climate. Seen together, they resemble forests of stone, where every trunk and branch was born from a single droplet falling through darkness, carrying the memory of rain and the passage of unthinkable time. Cave formations grow slower than fingernails. The breathtaking shapes found underground are products of unimaginable patience. Stalactites, flowstones, and crystal draperies accumulate one thin layer at a time as water leaves behind films of mineral. A single centimeter of growth can take hundreds of years. The rate depends on drip speed, mineral purity, and even the temperature of the surrounding rock. Some formations still glisten from drops that began their journey through the ground decades ago. Studying their layers lets scientists reconstruct past climates, revealing droughts, floods, and shifts in rainfall long before written history. Walking through a cavern can feel like stepping into a slow-motion clock, where time moves at the pace of minerals crystallizing. These subterranean sculptures remind us that beauty can arise not from speed or force, but from stillness and persistence beyond human measure. Some caves have their own weather systems. Deep underground, large cave networks can develop microclimates distinct from the surface. Temperature, humidity, and airflow combine to create fogs, winds, and even tiny clouds drifting through chambers. Warm air rising from deeper passages meets cooler air near entrances, producing swirling currents like miniature weather fronts. Some caves breathe on a seasonal rhythm, exhaling warm air in winter and drawing in cool air in summer. As outside conditions change, moisture condenses on walls and drips to sustain delicate formations and ecosystems. To step inside is to feel the planet inhale, air and rock join together. These hidden climates can preserve fossils, artifacts, and species that cannot survive elsewhere. Within their stone lungs, caves remind us that even Earth's most solid places are filled with movement, breath, and subtle patterns of living atmosphere. Earth's longest cave stretches for hundreds of miles underground. Beneath the rolling hills of Kentucky lies Mammoth Cave, the largest known cave system on Earth. Its passages extend for more than 400 miles, and new tunnels are still being discovered. The maze was carved by ancient rivers dissolving limestone over millions of years, branching and looping into a labyrinth that could hide entire cities. Explorers move through narrow crawls, towering chambers, and underground rivers that still reshape the rock today. The air stays cool and still, and the silence feels so deep it seems alive. The sheer scale challenges the imagination, reminding visitors how much of the planet exists unseen beneath our feet. Mammoth Cave is both a geological wonder and a living record of time, carved by water's persistence into a cathedral of stone that stretches into darkness without end. Earthquakes can permanently change the length of a day. When a massive earthquake shifts how Earth's mass is distributed, the planet's rotation changes slightly. The effect is tiny, usually measured in microseconds, but it can be measured. By moving enormous slabs of rock, a quake can alter the planet's moment of inertia, like a spinning skater speeding up when pulling their arms in. After the 2004 Sumatra earthquake, scientists calculated that the day shortened by a fraction of a second. The event also nudged the position of the poles and adjusted Earth's shape ever so slightly. These shifts remind us that even the idea of a day, which feels absolute, is influenced by deep movements of rock and gravity. Each quake is not only a surface event, but a planetary one, echoing into the rotation of the world itself and whispering change into the rhythm of time. Shockwaves from massive quakes travel all the way around the globe. When a powerful earthquake strikes, and the energy it releases doesn't stop at the epicenter. Seismic waves ripple through the entire planet, racing through crust and mantle like sound through a bell. Sensitive instruments can detect the same quake circling the world several times before fading. The largest events make the whole Earth tremble, subtly flexing the crust as energy crosses from one side of the globe to the other. Even regions thousands of kilometers away can register faint aftershocks. Scientists use these reverberations to map Earth's interior, tracing how waves bend and reflect inside layers, including molten regions. Each tremor reveals something about the deep Earth, where it is solid, where it flows, and how heat moves within. Every great quake briefly turns the planet into a single vibrating instrument, humming softly with its own heartbeat. And some earthquakes release energy equivalent to millions of tons of TNT. The scale of a major quake's energy is staggering. When the largest faults rupture, they can release power comparable to several million tons of explosive material detonating at once. The shaking we feel is only part of it. Much of the energy travels deep into the crust, shifting rock layers that outweigh entire mountain ranges. The moment magnitude scale used today was designed to measure these immense forces more accurately than older systems. During the 2011 Tohoku quake in Japan, the energy released was enough to alter Earth's rotation and shift the seafloor by several meters. Numbers like these are hard to hold in the mind, yet each quake reminds us that the crust is under constant stress, storing and releasing energy in a powerful rhythm that shapes continents and seas over time. Rocks deep underground can flow like putty under pressure. Stone feels rigid and unyielding to us, but deep inside Earth, it behaves differently. At great depths, where temperatures and pressures rise beyond imagination, rock begins to deform slowly, flowing like an extremely thick liquid. Over millions of years, this plastic movement allows whole mountain ranges to rise, fold, and transform. Minerals stretch and twist, creating the patterns we later see in metamorphic rocks exposed at the surface. In laboratory experiments, geologists have watched samples bend rather than break when heated and compressed, confirming that time itself changes how matter behaves. The mantle beneath our feet constantly moves this way, and its flow helps drive the drifting of continents above. And it's a reminder that even what seems rigid can move, and that the strength of stone lies not only in hardness, but in its ability to yield, reshape, and endure. Metamorphic rocks record the history of pressure and heat inside the planet. When rocks are buried deep in Earth's crust, they change. Immense heat and pressure reorganize minerals without fully melting the rock, creating new textures and structures. Granite becomes gneiss, limestone becomes marble, shale becomes slate. Each metamorphic stone carries a record of the forces that shaped it, like pages in a geological diary. Scientists read these signatures to reconstruct ancient mountain building and to estimate the depths where certain rocks once rested. Some metamorphic formations even revealed the direction of tectonic movement through mineral alignment. And when uplift finally brings them back to the surface, we glimpse Earth's internal history frozen into crystalline form. They are rocks that remember, preserving within their folds the immense energies flowing invisibly beneath the crust, showing that every mountain was once hidden, being rewritten by heat, pressure, and time. Slate was once mud pressed by time into stone. Beneath ancient seas, layers of mud settled in quiet darkness. Over millions of years, sediments compacted under the weight of new layers above, squeezing out water and aligning clay minerals into flat sheets. With enough heat and pressure, that mud hardened into slate, a rock so finely layered it can split into smooth tiles. The transformation is a story of stillness becoming strength, sediment reborn as stone. Slate once formed entire seafloors, and today it roofs cottages and lines pathways, carrying the imprint of ancient oceans into our modern world. If you hold a piece and tilt it in the light, you can still see the sheen of compressed minerals, tiny echoes of clay that once drifted lazily through water. It is proof that even the softest materials can, through time and pressure, become enduring and strong. Marble began its life as limestone filled with sea fossils, long before it gleamed in temples and sculptures. Marble started as humble limestone on the seafloor, built from shells and skeletons of marine life, coral, plankton, and mollusks, compressed over millions of years. When buried deep inside Earth, it met heat and pressure that enlarged its crystals, erasing visible fossils and creating marble's smooth, interlocking texture. Trace minerals added subtle colors. Iron for red, serpentine for green, graphite for gray. When polished, these minerals catch the light, giving marble its famous glow. Ancient civilizations prized it because it seemed to hold sunlight within. In truth, it is a relic of vanished oceans, born from life, death, and transformation. Every polished surface of marble, from a cathedral column to a carved statue, was once part of a living sea that hardened into timeless beauty. Every gemstone tells the story of its geological birth. Hidden deep in Earth's crust, heat, pressure, and chemistry collaborate to create crystals of astonishing beauty. Diamonds form under crushing forces hundreds of kilometers down, while emeralds grow in mineral-rich veins where water and rock trade elements. Rubies, sapphires, topaz, and quartz each arise from precise conditions of temperature and chemistry that rarely align. That rarity makes them precious. When cut and polished, Their clarity reveals the harmony of atomic structure, a glimpse of order forged in chaos. Gemstones travel from deep rock to human hands through volcanoes, erosion, and time. Each is a messenger from a different environment within the planet, a record of hidden processes. To look into a gemstone is to peer into Earth's memory, seeing the patience of pressure and the art of crystallization written in glittering symmetry. Rubies and sapphires are the same mineral, colored by different elements. At first glance, rubies and sapphires seem entirely different, yet both are varieties of the same mineral, corundum. In its pure form, corundum is colorless. It's made of aluminum and oxygen in a tightly packed lattice. When tiny amounts of chromium enter that structure, it glows red and becomes ruby. When iron and titanium take its place, the result is blue sapphire. Other trace elements can produce yellows, greens, or even pinks. These subtle substitutions change how light travels through the crystal, giving each gem its hue. The fact that two of the world's most prized stones come from the same mineral shows how small changes at the atomic level can create astonishing beauty. Every color is a fingerprint of chemistry, proof that nature's artistry begins in the invisible dance of elements deep within Earth. Emeralds form only under the rarest conditions of pressure and chemistry. Among gemstones, emeralds are among the most elusive, and they require a rare meeting of two different worlds, silica-rich rocks and beryllium-bearing fluids, conditions that seldom overlap. When they do, the mineral beryl forms, colored green by traces of chromium or vanadium. This delicate balance occurs only in certain mountain regions where tectonic activity has blended the ingredients. The result is a gem that carries the tension of its birth in every shimmering facet. Most emeralds contain tiny fractures and inclusions called jardin or gardens that record their natural formation. These are not flaws, but signatures, evidence the stone is a true child of Earth. To hold one is to hold the story of improbable chemistry, immense pressure, and geological patience conspiring to create something rare and luminous. Opal forms from ancient groundwater seeping through silica-rich rock. The opal is unlike most gemstones because it is not crystalline. It forms when water carrying dissolved silica trickles through rock, depositing microscopic spheres that stack in delicate layers. Those spheres scatter light, creating opal's rainbow shimmer. Its play of color. Many opal deposits began in landscapes that are arid today, but were once wet millions of years ago. As water evaporated, it left behind these intricate glowing structures. Under magnification, opal reveals order hidden within apparent chaos, a mosaic of color suspended in stone. Australia, home to some of the finest specimens, was once part of an ancient inland sea where these processes unfolded. Every opal captures not only the light we see, but the memory of vanished rain, lost rivers, and quiet chemistry that turns water and sand into fire frozen within stone. Meteorites on Earth tell stories from before our planet was born. When fragments of rock fall from space, they bring messages from the earliest days of the solar system. Some meteorites formed billions of years ago, before Earth existed, from the same cloud of dust and gas that birthed the sun and planets. They contain minerals unchanged since that time, preserving a record of ancient chemistry. Scientists study them to learn how planetary building blocks assembled, melted, and separated into cores and crusts. Some even carry organic compounds, hinting that the ingredients for life were scattered through space long before Earth took shape. To hold a meteorite is to touch something older than our world, a piece of cosmic debris that crossed time and distance to rest in our hands, carrying the memory of creation itself. Some rocks are older than the solar system itself. Within certain meteorites, scientists have found microscopic grains called pre-solar dust, remnants of stars that lived before our sun. These tiny crystals formed in the outer layers of dying stars and were thrown into space on stellar winds. For billions of years, they drifted through the galaxy, eventually becoming trapped in the material that built our solar system. Their isotopic fingerprints reveal alien origins, unlike anything naturally produced on Earth. To discover such grains inside a rock is to find stardust untouched by planetary cycles, matter that predates the world itself. When we analyze these particles, we read stories written before the sun rose, echoes of supernovae, and the slow breath of red giants. Each grain is a whisper from the galaxy's past, a proof that Earth itself was born from recycled stars. Lunar rocks brought back by astronauts help date Earth's early crust. Samples collected during the Apollo missions revealed more than the Moon's history. They illuminated Earth's beginnings. The isotopic composition of lunar rocks closely matches Earth's mantle, supporting the idea that the Moon formed from debris after a colossal collision between young Earth and another planet-sized body. By studying those samples, scientists estimated when Earth's crust first solidified, around 4.5 billion years ago. Some of the oldest lunar basalts also record impacts that shaped the early solar system. The Moon's surface, pitted by micrometeorites, has remained largely unchanged for eons, preserving a bombardment record lost on our eroded planet. Every moon rock brought home is a time capsule, linking two worlds forever, joined by a single violent origin story written in dust and fire. The oldest minerals ever found are tiny zircons from ancient Australia. In the ancient rocks of Western Australia, geologists discovered microscopic zircon crystals older than 4 billion years. These resilient minerals formed soon after Earth itself and survived countless cycles of erosion and metamorphism. Inside each lies trace uranium that decayed into lead, allowing scientists to measure its age with extraordinary precision. The zircon's chemistry suggests liquid water already existed when it formed, meaning Earth's surface cooled surprisingly quickly after its violent birth. These crystals are among the few surviving witnesses of the planet's earliest chapter, fragments that outlasted the destruction of entire continents. And to view a zircon under a microscope is to look into the dawn of Earth's history, a crystal memory from a time when oceans, crust, and atmosphere were still taking shape. These zircons record the first liquid water on Earth. Analysis of the ancient zircons revealed chemical ratios consistent with rocks that had interacted with liquid water. That finding pushed the timeline for Earth's oceans far earlier than once believed, perhaps within 200 million years of the planet's formation. Before this, scientists often pictured early Earth as molten for far longer. The zircons suggested the surface cooled enough for rain, rivers, and seas remarkably soon. This realization reshaped our understanding of habitability, implying that life-friendly conditions may have appeared quickly. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival. Through them, we glimpse a world where vapor condensed, clouds gathered, and the first rain fell onto cooling stone, the beginning of the blue planet we know today. The continents were once covered in lava fields the size of countries. Throughout deep time, enormous volcanic events known as flood basalt eruptions blanketed vast regions of Earth in sweeping sheets of molten rock. These outpourings sometimes continued for millions of years, building plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan Traps in India and the Siberian Traps in Russia are two dramatic examples. Such eruptions released immense volumes of gas into the atmosphere, reshaping climate and ecosystems. When the lava cooled, it left behind stepped landscapes and fertile soils that still influence agriculture today. To stand atop one of these regions is to stand on frozen lava that once ran like rivers of fire, rewriting continents. These basalt fields remind us that Earth's calm present hides a fiery past, when entire provinces pulsed with magma and the air shimmered with volcanic light. Those lava floods have caused mass extinctions in the past. The greatest outpourings didn't only reshape continents, they reshaped life itself. The gases and ash released during flood basalt events can poison the air, dim the sky, and disrupt climate for thousands of years. The Siberian Traps eruption around 250 million years ago coincided with the greatest extinction in Earth's history, wiping out most marine species and many on land, and catastrophic releases of carbon dioxide and sulfur dioxide triggered acid rain and intense warming, unraveling ecosystems. Yet after the devastation, life eventually returned and diversified, adapting to the altered world. These cycles of ruin and renewal are woven into Earth's long story, proof that even the darkest chapters become the groundwork for what follows. In every extinction lies a seed of evolution, a silent transformation written in ash and stone. Ash from ancient eruptions still lies buried in modern soils. Across the world, thin layers of volcanic ash are preserved within sediment and ground, quiet records of eruptions thousands, even millions of years old. Each layer can be traced to its source volcano by the distinct chemical signature of its minerals, and are letting scientists match far-flung sites and build precise timelines of the past. Farmers sometimes unknowingly mix these ancient ashes into their fields, and the minerals can enrich soil with nutrients. In places like Italy, Iceland, and Japan, volcanic deposits have made land extraordinarily fertile. To dig into such earth is to touch history, the residue of fire transformed into life. The same ash that once blotted out the sun now feeds crops and forests, completing a cycle where destruction nourishes creation, and the remnants of catastrophe sustain the quiet persistence of growth. The Atlantic Ocean was once just a long rift valley. Before the ocean we know existed, the lands that became Africa and the Americas were fused within a single supercontinent. Deep cracks began opening between them around 200 million years ago, forming a vast rift that slowly filled with water as the continents pulled apart. Over millions of years, volcanic activity widened the gap, and a new ocean was born. The Mid-Atlantic Ridge, where new crust still forms today, marks the original line of separation. Ancient rift valleys like those in East Africa offer glimpses of what the early Atlantic once resembled: long depressions scarred by faults and threaded with rising magma. What is now an ocean began as a fracture in Earth's crust, proof that even immense seas start as narrow wounds in stone, deepening until they become worlds of their own. The seafloor spreads outward from the mid-Atlantic ridge like a conveyor belt. In the center of the Atlantic lies a mountain chain hidden beneath the waves, where fresh crust is continuously made. Magma rises through cracks, cools, and steadily pushes older rock aside in a symmetrical flow. As this happens, continents on either side drift farther apart, carried by the movement of the seafloor itself. Magnetic minerals in the cooling lava align with Earth's magnetic field, creating striped patterns that record ancient reversals. By measuring these stripes, scientists confirm the seafloor truly spreads, strengthening the case for plate tectonics. The process continues at only a few centimeters per year, imperceptible yet unstoppable. This underwater conveyor of creation expands the ocean, even as older crust is pulled down at subduction zones elsewhere, keeping Earth's surface in constant living motion. Hydrothermal vents create black smokers on the ocean floor. Deep beneath the ocean, along ridges where tectonic plates meet, seawater seeps into the crust through cracks and fissures. It sinks until it nears molten rock, heats to hundreds of degrees, then rises again loaded with dissolved metals and minerals. When that superheated water bursts into the cold sea, it cools instantly, forming dark clouds that billow upward like smoke. These black smokers are underwater chimneys of heat and minerals, forever forming and collapsing. They build mounds rich in iron, sulfur, and other compounds that glint faintly in the deep. Around them, the water shimmers with suspended particles, and a strange kind of life flourishes, fed not by sunlight, but by chemistry. Each vent is a miniature world, a living reminder that even in eternal darkness, the planet can breathe, burn, and build. Those vents support entire ecosystems without sunlight. Far from the reach of daylight are life clusters around deep-sea hydrothermal vents in dense colonies. Here, instead of photosynthesis, organisms rely on chemosynthesis, bacteria using chemical energy from sulfur and methane to produce food. Giant tube worms, clams, crabs, and fish depend on these microscopic producers, forming ecosystems unlike any other on Earth. Temperatures near the vents can swing from near freezing to over 300 degrees Celsius within meters. Yet life not only survives, it thrives. The discovery of these communities in the 1970s changed biology forever, showing that life does not require sunlight, only energy and water. Scientists now suspect similar environments could exist on icy moons like Europa and Enceladus. The once assumed barren seafloor hums with life powered by Earth's heat. A partnership between geology and biology still unfolding. And minerals there build chimneys taller than houses. At vent sites, minerals continuously precipitate from the superheated fluids streaming into the ocean. Over time, they accumulate into towering chimneys that can rise more than 20 meters high. These structures grow upward as long as the flow persists. Layer upon layer of sulfides and other minerals stacking into intricate columns like cathedrals in the deep. Some collapse under their own weight, only to be rebuilt again. Within these formations, metallic ores concentrate, similar to the kinds humans mine on land. Their shimmering surfaces host communities of microbes and animals adapted to searing temperatures and chemical gradients. The vents pulse like underwater volcanoes, their chimneys smoking gently in the dark. They are proof that even in extreme environments, Earth sculpts beauty from pressure and heat, crafting elaborate monuments few eyes will ever see directly. Earth's magnetic field has flipped hundreds of times throughout its history. The planet's magnetic poles have reversed again and again, swapping north for south. These flips occur irregularly, sometimes separated by hundreds of thousands of years, sometimes by millions. The cause lies deep in the molten outer core, where currents of liquid iron generate the magnetic field. As those currents shift, the field weakens, reorganizes, and eventually reverses. Evidence of this constant flipping is written into volcanic rocks, especially on the seafloor, where iron minerals align with the magnetic field as lava cools. Each band of opposite polarity marks a moment in that long cycle. A reversal can take thousands of years to complete, whilst yet life has persisted through everyone without collapse. The phenomenon reminds us that even the invisible shield protecting Earth from cosmic radiation is dynamic, a living force shaped by the motion of the planet's molten heart. During those flips, compass needles would have pointed south. If you could stand on Earth during a period of reversal, your compass would gradually start to drift and confuse. Over centuries, magnetic north would wander toward the equator, cross it, and eventually point roughly south. The change unfolds slowly as the field weakens, splits into multiple poles, and then reforms in the opposite direction. Rocks preserve the memory of such shifts, their magnetic minerals frozen in whatever direction was north at the time they formed. By studying these ancient orientations, scientists reconstructed reversal timelines and tracked the wandering of poles through deep time. Though it may sound unsettling, reversals are normal and common in Earth's past. They have not triggered mass extinctions or caused the atmosphere to fail. Instead, they reveal the vitality of the geodynamo, the deep engine that keeps Earth's magnetic heart beating across the ages. Even today, the magnetic poles wander by miles each year. Earth's magnetic field is not fixed. The North Magnetic Pole, once in the Canadian Arctic, is now racing towards Siberia at a pace exceeding 30 kilometers per year. This drift happens because the molten iron in the outer core is constantly moving, shifting the balance of magnetic forces. Satellites track the pole's motion continuously, and navigation systems are updated as its position changes. While magnetic north wanders, geographic north remains steady, making the 2 points distinct. Most people never notice the difference, but to scientists, the shifting pole is a reminder that the field protecting our atmosphere is alive and evolving. The invisible motion that guides compasses also reveals the slow liquid heartbeat of the world beneath our feet. The moon stabilizes Earth's wobble, which shapes long-term geology. Without the moon's steadying pull, Earth's tilt could vary far more dramatically over time, swinging from near upright to steep angles. Such instability would drive chaotic climate shifts, turning frozen poles into tropical zones and back again. The moon's gravity keeps Earth's axial tilt within a narrower range. This stability has allowed long geological and biological cycles to develop, supporting consistent patterns in ocean currents, ice ages, and weather. The tides raised by the moon also redistribute energy through the oceans, influencing erosion and the movement of sediment along coasts. Much of Earth's balance, its blend of order and change, owes something to that silent companion overhead. Every gentle tide and reliable season is, in part, a gift from the moon, guiding Earth's dance for more than 4 billion years without missing a single step. Tides caused by the moon sculpt coastlines across millennia. Each day the sea rises and falls as lunar gravity tugs on Earth's waters. Over years and centuries, tides do more than move waves. They reshape shorelines. Tidal forces carve estuaries, widen bays, and transport sediments that build beaches and deltas. They erode cliffs and carry nutrients that sustain marine life. And in some regions, tidal ranges exceed 10 meters, creating wide intertidal zones that alternate between land and sea. These shifting environments become nurseries for fish, birds, and countless invertebrates. Over geological time, tides have influenced continental shelves and helped form barrier islands. The rhythm is ancient and persistent, tying distant celestial motion to the patterns of sand beneath our feet. The shoreline we see today is a moving sculpture, shaped grain by the patient breath of the moon. Coral reefs are living geological structures made of calcium skeletons. Coral reefs, though crowded with life, are also immense geological constructions. Each coral polyp builds a tiny limestone skeleton, and generation after generation stacks these structures upward towards sunlight. Over thousands of years, the result becomes a reef so vast it can be seen from space. The Great Barrier Reef, for example, stretches over 2,000 kilometers, formed layer by living builders. When corals die, new corals grow atop their remains, and the building continues. Reefs act as natural breakwaters, protecting coastlines, and as archives of ocean history, storing temperature and chemistry in their layers. Even fossil reefs tell stories of ancient seas that once covered modern continents. Every coral colony is both a biological community and a geological monument, living rock that breathes, grows, and preserves the memory of oceans that shaped our world. Some coral reefs are older than many mountain ranges. Beneath calm tropical waters are reefs that have been growing for tens of millions of years, and some began when dinosaurs still walked the land. Over those spans, whole mountain chains have risen and eroded away, while these underwater structures quietly expanded. Their cores are compacted limestone, made from the skeletons of billions of tiny organisms. As sea level rose and fell, reefs adapted, climbing upward or shifting toward the light. Fossil remnants of ancient reefs now appear in deserts and on mountaintops, proof that what was once seabed can become land. The endurance of reefs shows continuity through upheaval, their layered skeletons tracing biological and geological time together. Each one is a cathedral of life and stone, older than civilization, older than many mountains, a living bridge across eras of Earth's unfolding story. Dust from deserts can fertilize entire rainforests across oceans. Tiny grains of mineral dust, lifted from great deserts, travel thousands of kilometers on high winds, crossing continents and seas. Much of this dust eventually falls on distant ecosystems, delivering vital nutrients. The Amazon rainforest, for instance, depends on phosphorus-rich dust carried from the Sahara to replenish its soils. Without that input, heavy tropical rains would wash essential minerals away. These airborne particles connect ecosystems that seem unrelated, linking arid wastelands to lush jungles. Satellite images have captured vast plumes crossing the Atlantic, glowing in sunlight before settling as invisible nourishment. Each grain is a geological traveler, a fragment of rock that left one landscape to sustain another. In this quiet exchange, deserts and forests become partners in a cycle of erosion, wind, and renewal spanning the whole globe. Rocks on Earth contain tiny fragments of stardust inside some meteorites, and even within certain ancient terrestrial rocks lie microscopic grains that formed in dying stars long before the solar system existed. These specks survived the collapse of the cloud that birthed the sun and became part of the material that built the planets. Their isotopic signatures are unlike anything produced on Earth, marking them as truly alien. When scientists isolate these particles, they can trace stellar life cycles from formation to explosive endings. Each grain holds atoms forged in stellar furnaces, proof that everything on our planet, including us, once belonged to the cosmos. These fragments bridge time and distance, reminding us geology is not only an Earth story, but part of a universal tale of matter, forever changing through creation and decay. Gold and platinum came from ancient meteor impacts. The precious metals used in jewelry and technology were not all part of Earth's original crust. During formation, most gold, platinum, and other heavy elements sank into the molten core. Much of what we mine near the surface arrived later, delivered by meteorites during a period of intense bombardment more than 4 billion years ago. Those impacts scattered metallic debris across the surface, enriching the upper crust with treasures forged in stellar explosions. Every gold vein and platinum deposit is a cosmic inheritance, the residue of cataclysm that once lit the early solar system with fire. To hold a piece of gold is to touch the memory of that ancient rain of metal from the stars, a tangible link between celestial violence and earthly beauty. Some impact craters are so eroded they're almost invisible. Over millions of years, wind, water, and tectonic motion can erase most signs of a meteor strike. What begins as a vast circular crater slowly fills with sediment, its rim softened, its scar hidden beneath forests or seas. Yet clues remain in the rock: shocked quartz, melted minerals, and buried rings of fractured crust that betray a violent origin. Scientists use satellite imagery and magnetic surveys to find these concealed wounds, many of which once held lakes or even supported human settlements, unaware of their cosmic foundations. Across North America, Africa, and Australia, ancient craters lie beneath younger layers, some dating back billions of years. Their near invisibility shows how Earth heals, smoothing even deep wounds until they blend into the land around them. One giant impact may have triggered the age of the dinosaurs. Around 200 million years ago, a massive asteroid may have struck Earth near what is now Canada, coinciding with the end Triassic extinction event. The collision released enough energy to darken skies and ignite fires across continents. Volcanic activity followed, and global temperatures swung sharply. Many reptile groups vanished, while dinosaurs, better suited to the changed world, rose to dominance. The crater left behind, though heavily eroded, still holds traces of melted rock and shocked minerals, preserving a story of destruction and recovery. Impacts like this have repeatedly reset evolution, ending some lineages while opening space for others. In the wake of chaos, ecosystems rebalance and new forms of life emerge. From upheaval, the great rulers of the Mesozoic rose, only to be ended by another catastrophe. Another may have ended it. 66 million years ago, an asteroid about 10 kilometers wide struck what is now Mexico's Yucatan Peninsula, releasing energy equal to billions of atomic bombs. The impact vaporized rock, ignited global wildfires, and lofted dust high enough to block sunlight for years. Photosynthesis collapsed, food webs failed, and more than 70% of species disappeared, including the non-avian dinosaurs. The crater it left, Chicxulub, remains buried beneath limestone, yet its shape is remarkably preserved. Beneath the rim lies evidence of immense heat and pressure, a frozen record of one of Earth's most violent moments. And yet from that extinction came the rise of mammals and, eventually, humans. The event that ended one era began another, showing how destruction and creation intertwine in the planet's turning wheel of change. Earth's surface is dotted with hidden scars from ancient collisions. While some craters are obvious, countless others lie buried beneath oceans, deserts, or layers of younger rock. Geologists detect them through subtle gravitational and magnetic anomalies that reveal circular patterns deep below. Some hidden scars are so old they reach back to Earth's earliest eons, when impacts battered the young planet, reshaping crust and perhaps delivering water and carbon crucial for life. These wounds, though concealed, are part of the ground beneath us, quiet evidence of a turbulent cosmic youth. Each discovery reminds us that the world we call stable has endured unimaginable violence. Erosion and plate motion may erase the surface marks, but deep in stone, the memory remains, waiting to be read by those who listen. Even today, space dust adds hundreds of tons of new material each day. Earth still grows, grain by grain. Every day, tiny particles of cosmic dust drift into the atmosphere, flaring briefly as meteors or settling quietly onto land and sea. Scientists estimate that more than 100 tons of this material accumulates daily. Much of it comes from comets and asteroids shedding fragments as they orbit the sun. Collectors in Antarctica and even on rooftops have gathered microscopic spheres of interplanetary dust, with their metallic skins glinting under microscopes. Over billions of years, this steady fall has slightly increased Earth's mass, even as erosion and escaping gases remove some. These particles remind us the planet remains connected to the wider cosmos, continuously trading matter with the universe, a gentle, ceaseless rain of stars. Geology links every mountain, ocean, fossil, and living thing in one story. Earth's history shows that nothing stands alone. The forces that lift mountains also stir seas, recycle rock, and shape conditions for life. Fossils reveal how climate and geography guided evolution, while minerals record the deep processes that built continents. Every river carries the signature of erosion, and every grain of sand was once part of stone. Over billions of years, plate movement, volcanism, and weathering have woven an unbroken narrative, tying land, life, and time together. Geology is the language of that narrative, the script written in layers beneath our feet. It reminds us the world is both ancient and alive, and that by studying Earth, we read the planet's autobiography. The rocks beneath our feet are the planet's memory written in stone. Every pebble, cliff, and mountain is a page in Earth's vast diary. Within their grains are records of ancient seas, eruptions, ice ages, and the slow drift of continents. Radiometric clocks measure their ages, while fossils and mineral patterns reveal climates and creatures that came before. Rocks remember heat and pressure, flood and drought, creation and decay. Together, they form a grand archive of time, evidence that the world is always moving, yet endlessly patient. And standing on solid ground can feel like permanence, but in truth, we stand on history in motion, a crust forever forming, breaking, and reforming. To listen to Earth is to hear its long, quiet memory, the murmur of stone recording a world that has never stopped changing, growing, and remembering itself. The world beneath you is always moving. Even now, as you rest, the ground turns slowly under stars that once forged the minerals in your bones. Beneath the quiet crust, molten rock circulates in endless cycles, shaping continents that drift like slow clouds across a sea of stone. Geology teaches that change doesn't always roar. Most of it whispers. Mountains rise grain by grain. Oceans widen beyond memory. Every pebble, crystal, and grain of sand carries time so vast, our own stories feel like brief flashes. Yet those flashes belong to the same pattern written into the planet's fabric. Somewhere deep within Earth, pressure builds. Somewhere else it releases, and a new rock begins its long transformation. Far above, wind grinds stone into dust, and that dust crosses oceans to feed life. Everything that was becomes something new again. The planet breathes in the slow rhythm of stone, and we breathe with it without noticing. You might think of the places you have walked, the sound of gravel underfoot, the rough face of a cliff, the warmth of sand slipping through your fingers. Each is a story told in minerals, shaped by time and touch. The world is not only alive on its surface, it lives within itself, turning memory into matter, silence into form. As you drift towards sleep, let that thought sink like rain into soil. Imagine the deep pulse beneath you, ancient and steady. Let it quiet your mind and slow your breathing. You are part of this story too, a brief moment in a vast, unfolding world that remembers everything. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy. Let the planet cradle your thoughts, still patient, still eternal. Sleep well and good night.